Continuing on Physical Chemistry, Chapter 17, we're in Section 6 now. We're going to talk about reaction mechanism some more. So, a mechanism is a very hypothetical statement, but it has to be based on evidence. So, first of all, let's talk about the rate determining step approximation. This is also called the equilibrium approach. So, let's use a mechanism to determine a rate law. For example, let's say we have H plus ions plus HNO2 plus aniline. Remember, Phe is a phenyl group, so it's a C6H5. And then we have a catalyst of bromide, so we're going to get this phenyl group with N2 plus, so this is diazonium salt plus H2O. So this phenol plus N2 plus, that's diazonium salt right there. So R is equal to K times the concentration of the H plus ions plus the concentration of the HNO2 times the concentration of the bromide ions. Now this is observed, it's experimental. And like I said before, the bromide is a catalyst. Now how exactly is it happening? We're going to have this proposed mechanism that's based on the experimental rate law. So first we'll say that an H plus ion, it reacts or collides with a nitrous acid. So we have H plus HNO2 in equilibrium with this H2NO2 plus. And of course there'll be a forward rate constant and a reverse rate constant for this equilibrium reaction. And we'll say this one happens really fast. And then step 2, we'll take that H2NO2 plus a bromide and go into ONBr plus H2O. So we're going to say this is much slower than this, therefore this is the RDS, the rate determining step. Now this ONBr, this nitrosyl bromide. And then third, we're going to have the ONBr plus this phenyl NH2 going to phenyl N2 plus H2O plus bromide. And we'll say this is much faster than the middle step here, which is why the middle step is the rate determining step. And of course, there will be a rate constant for this reaction too. So if we add up both sides of all these reactions, then adding up the steps in the mechanism should give the original reaction. So in this case it does. So we can say that the mechanism is plausible so far. Now also the rate determining step should have the same rate law as the overall reaction. Now to find the rate law, look at the rate determining step. So in this example it's step 2. So we have R is equal to K2 times the concentration of the H2NO2 plus times the concentration of the bromide ions. So remember, this H2NO2 plus is an intermediate. Now, we can't have an intermediate in the rate law. We need to do the rate law based on reactants or products or catalysts or something. So we're going to say Kc is equal to K1 over K minus 1, and that's equal to the concentration of H2NO2 plus divided by the concentration of H plus times the concentration of HNO2. So we're going to solve that and for HNO2 plus. So we have the concentration of HNO2 plus is equal to K1 over K minus 1 times the concentration of H plus times the concentration of HNO2. So then we have R is equal to K2 times K1 over K minus 1 times the concentration of H plus times the concentration of HNO2 times the concentration of the bromide. So then we get R is equal to K times the concentration of H plus times the concentration of HNO2 times the concentration of the bromide. So we combine those three constants. So this is our deduced rate law. So this is our rate law based on the proposed mechanism. Now the rate law based on the proposed mechanism matches the experimental rate law in this case. So we can continue to say that the mechanism is plausible. Now a second way is called the steady state approximation. Now this will lead to a complicated rate law. It's also called the stationary state approximation. Now we're going to use capital I to represent an intermediate. So we're going to say that the derivative of the concentration of I with respect to T is equal to 0 for each intermediate. So here's some examples of what we want to do. We have H plus HNO2 in equilibrium with the H2NO2 plus. Again, that was fast. And then we're going to have the H2NO2 plus the bromide is going to go to the ONBR plus H2O. That was our slow step. And then we have the ONBR plus the phenyl, what is that, aniline or whatever, going to K3 phenyl N2 plus H2O plus the bromide, another fast step. So in this example mechanism, the ONBR and the H2NO2 plus are intermediates. And then we have R is equal to K3 times the concentration of the ONBR times the concentration of the phenyl NH2. That's equation 1. Now what we need to do is substitute for the concentration of the ONBR since it's an intermediate. Now remember, for the steady state approximation, we don't need to know which steps are slow and fast, actually, because that's for the rate determining step approximation. So we have the derivative of the concentration of the ONBR with respect to time is equal to K2 times the concentration of the H2NO2 plus times the concentration of the bromide minus K3 times the initial concentration of the ONBR, or just concentration times the concentration of the phenyl NH2. That's equal to 0. So now we're going to solve for ONBR. So we get the concentration of the ONBR is equal to K2 over K3 times the concentration of H2NO2 plus times the concentration of the bromide divided by the concentration of this phenyl NH2, whatever you call it. So substitute that into equation 1. So we get R is equal to K3 times K2 over K3 times the concentration of H2NO2 plus times the bromide times the concentration of that phenyl NH2 divided by the concentration of the phenyl NH2. These two are the same, so they're going to cancel out. And these K3s cancel out. So we just end up with R is equal to K2 times the concentration of the H2NO2 plus times the concentration of bromide. That's equation 2. But also notice that this H2NO2 plus is an intermediate. So again, we need to substitute out. And we're going to apply the steady state approximation again. So we get the derivative of the concentration of the H2NO2 plus with respect to time is equal to K1 times the concentration of H plus times the concentration of HNO2 minus K1 times the concentration of H2NO2 plus minus K2 times the concentration of H2NO2 plus times the concentration of bromide, and that's equal to 0 because it's a steady state approximation. So again, we're going to solve for this concentration of H2NO2 plus. So we get H2NO2 plus, the concentration, is equal to K1 times the concentration of H plus times the concentration of HNO2 divided by K minus 1 plus K2 times the concentration of the bromide ions. So we're going to substitute that back into equation 2. Then we get R is equal to K2 times K1 times the concentration of H plus times the concentration of HNO2 times the concentration of bromide divided by K minus 1 plus K2 times the concentration of bromide. So as you can see, the rate law from the steady state approximation is usually more complicated than from the rate determining step method. So if K minus 1 is much greater than K2, then K1 plus K2 down here, this bottom term here, is going to be roughly equal to K minus 1. So we'll simplify and say R is equal to K2 times K1 over K minus 1 times the initial times the concentration of H plus times the concentration of HNO2 times the concentration of bromide. And so we'll just say that K is equal to K2 times K1 over K minus 1. So we get R is equal to K times the concentration of H plus times the concentration of HNO2 times the concentration of bromide. That's the third order reaction. Now if K2 is much greater than K minus 1, then what will happen is we'll get R is equal to K1 K2 times H plus times HNO2 times bromide concentration of bromide, divided by K2, plus the Kr. Oh, this should be K2, right? I think that's a typo. Holy cow. Yeah, that should be K2. Hold on. Oops. Okay, K2 times the concentration of bromide. So then these K2s are going to cancel out. Okay, something went wrong here. Okay, I'll have to figure that out later. So R is equal to K1 times the concentration of H plus times the concentration of HNO2. Somehow I got an extra K2 on the bottom here. Okay, so this is going to be second order, and that's going to be K is equal to K1. So if possible, because it's so complicated, try to avoid the steady state approximation.